everyone. In this video, we are going to be looking at the base strength determination. So just like how we determine acid strength, we also can determine the base strength using a base dissociation constant. And in this case, we're looking at how the tendency of the dissociation of base into hydroxide ions. So for the base dissociation constant, over here is the equation that defines it. And for this equation, we can again write a equilibrium expression for the base dissociation constant. And over here, the way how this arises is similar to that of the acid dissociation constant. So I will not be going over it. I will just present you with the results. So it's going to be the concentration of the conjugate acid at equilibrium multiplied by the concentration of the hydroxide ion at equilibrium divided by the concentration of the base at equilibrium. And again, the higher Kb, the stronger acid. So higher Kb, that means that it has a higher rate of dissociation. So when it dissociates more, then it is a stronger base. So again, over here are examples as to how we can find Kb from the equilibrium concentrations. And again, I hope at this point you are more confident in pausing the video and trying out yourself. Caffeine C8H10N4O2 is a weak base. What is the value of Kb for caffeine if a solution at equilibrium has the concentration as follows? So looking at this, we know that Kb, the base dissociation constant, can be calculated by having the conjugated acid of the base multiplied by the hydronium ion concentration divided by the concentration of the base. So in this case, the first thing we have to do is to identify who is who. So we know the concentration of the OH at equilibrium. So remember, all of these concentrations are at equilibrium. And for the concentration of the conjugated acid, it is going to be this one because as we can see when we are comparing these two, the bottom one has an extra H+. So that means that it is the conjugated acid. And this one will be the base. So after identifying them all we have to do is to plug in the numbers. So that is going to be 5.0 times 10 to the negative third multiplied by 2.5 times 10 to the negative third divided by 0.050, and that is 2.5 times 10 to the negative 4. And again, it has no unit. And I guess the more challenging part of this is not the math part, is being able to identify who is the conjugated base or conjugated acid, who is the acid and the base. What is the equilibrium constant for the ionization of HPO4 2- ion, a weak base, if the composition of the equilibrium mixture is as follows? Looking at this, we know that the first thing we can see is that this particular equation is when we have hydrogen phosphate in water acting as a base, because it is gaining a proton while water is losing a proton. So this is acting as a base. And then the equilibrium constant for this particular reaction is the right side over the left side. So it's the concentration of OH multiplied by the concentration of the dihydrogen phosphate ion divided by the concentration of the hydrogen phosphate ion. And water is a liquid, so it's not part of it. And this resembles the base dissociation constant formula where the Kb is equal to the concentration of OH multiplied by the concentration of the conjugated base divided by the concentration of the base. So again, we can see that this is a base, it becomes its conjugated acid. So this is its conjugated acid, and then we have the hydronium ion. So essentially we're calculating Kb. And all we have to do now is to plug in the corresponding equations, corresponding values. So the concentration of hydronium ion, the concentration of the dihydrogen phosphate, and then the concentration of the hydrogen phosphate ion. So over here we have the OH minus 1.3 times 10 to the negative 6 multiplied by 0.042 divided by 0.341. And that is going to equal to 1.6 times 10 to the negative 7. So it's negative 7. And it has no units because it's an equilibrium constant. And here are how we can determine the concentration of hydroxide ion from the base dissociation constant. Find the concentration of hydroxide ion in a 0.25 molar solution of triethylamine, a weak base. The reaction is as follows. So in order to find the concentration of hydroxide ion, we are going to need to use the ice table. So we are again going to start by setting up the ice table, and we have the following information. CH3 and then OH minus. And the H2O is again omitted. So for the initial concentration, it is going to be 0.25 molar, and the initial concentration for the cation and anion is going to be 0. We have negative x plus x plus x, and 0.25 minus x, x, x. So all you have to do is to solve for x right now, and that is going to be like this. So remember that Kb is essentially specific to the reaction over here where the substance is acting as a base in water. So it is K, but if let's say if it doesn't give you this equation and it just tells you the Kb, you are expected to be able to write this equation out because you can predict the behavior of acids and base. So that's going to be x squared divided by 0.25 minus x. So this is x times x. And that is again going to be. So to solve for x, we know that x is going to equal to 0.00394. That is one of the possibilities. And the other one is negative 0.004, but again, we're not going to be using the negative value. With the x, we can know that we have the equilibrium concentration of the hydroxide ion because x is equal to the equilibrium concentration of the hydroxide ion. So our equilibrium concentration of the hydroxide ion is therefore going to be 0.00394 molar from the ice table. And remember that when it is asking you to find the concentration of hydroxide ion, since hydroxide ion is not present at the beginning, it is basically saying that we're needing to find the equilibrium one. So once the hydroxide ion is being produced, per se, and being stabilized. Oh, the concentration is stabilized. And over here we have an example as to how we can find the pH or pOH from the base dissociation constant. Again, hopefully at this point you're going to feel like, okay, I know how to do these, and these are relatively repetitive because we did that multiple times. But again, if you're not confident, then hopefully that by the next example you will feel a little bit more comfortable about what you're doing. Calculate the pH in a 0.01 molar solution of caffeine, a weak base. Looking at this, we know that we have a Kb for the reaction that is expressed on the left side, and in order to calculate the pH, we have to know the concentration of the hydronium ion, which can be found from the concentration of OH minus, because OH minus is part of the equation. So we have to first start by finding the equilibrium concentration of OH minus in order to find the pH. To do this, we will start with the ice table. So we will write down the caffeine and omitting the water, and also the ionized caffeine, and then OH minus, set up the ice table. So this part, again, I am hoping that by this point you are basically a pro at doing the ice table. Oops. And we can solve for x. So KB is going to equal to everything on the right side, so x times x, divided by everything on the left side. So that is this times this divided by this. So again, the KB has to be expressed using the equilibrium concentrations. So that is going to be 2.5 times 10 to the negative 4 is equal to x squared divided by 0.010 minus x. And we can solve for x to be 0.00146. And the other answer from the quadratic equation is negative 0.00171. Again, we know that it's not the case because it's a negative number. With the x, we can determine the concentration of the hydroxide ion at equilibrium because we know that the concentration of the hydroxide ion at equilibrium is x. So this part, we always do this part just to reiterate that, but there is not really a calculation associated with it. So to calculate the pH from OH, we have two ways. We can find the concentration of hydronium ion and then go to pH, or we can do the POH and then pH. So I will go to find the POH first and then the pH. So for the POH, it is equal to negative log of the concentration of the hydroxide ion, which is negative log of 0.00146. So this number, the hydroxide ion concentration at equilibrium, and that is going to equal to 2.84. And we know that pH plus POH is equal to 14. So the pH can be found by 14 minus 2.84. That is going to be 11.16. So POH is this number and it's that number. And this is our last one going the reverse direction. The pH of a solution of household ammonia, a 0.950 molar solution of NH3 is 11.612. What is the KB of NH3? So the first thing we know that we have to do is, again, because we're looking for KB, so we have to start by writing the expression of ammonia with KB. And that is essentially for KB, by definition, it is the substance acting as a base, so ammonia acting as a base in water. Okay, I will write it up here. And then it is going to act as a base to gain a proton, and water will be acting as an acid to lose a proton. So this is the reaction that we're looking at. And we know that this is the initial concentration of the base, and the pH allow us to find the concentration of the hydronium ion, which can let us find the equilibrium concentration of the hydroxide ion. So for first thing we have to do is to find the equilibrium concentration of the hydroxide ion, which we can start by, we know that 10 to the negative pH is equal to the concentration of the hydronium ion, so 10 to the negative 11.612 is equal to 2.44 times 10 to the negative 12 molar. And we know that Kw is equal to the concentration of the hydronium ion multiplied by the concentration of the hydroxide ion. So 1.0 times 10 to the negative 14 is equal to 2.44 times 10 to the negative 12. This is what we found over here. And the 1.0 times 10 to the negative 4 is a constant, the water dissociation constant, multiplied by the concentration of the hydroxide ion. And so we can find the concentration of the hydroxide ion to be 0.00410. So that is the equilibrium concentration of the hydroxide ion, and we can use this to complete our ice table. Looking at the ice table, we know that the reaction, as previously discussed, looks like this. And again, water is a substance on the left side, but we are going to omit that for the purpose of the ice table. Okay. So for the initial concentration of ammonia, it is 0.950. For the equilibrium concentration of OH minus, as we calculated from the pH in the previous step, it is going to be 0.00410. And to find Kb, we are going to need the equilibrium concentration of the OH minus, the equilibrium concentration of the ammonium ion, and the equilibrium concentration of NH3. So to start, we can again fill out the ice table and solve for X. So the first thing we have to do is to solve for X. So in this case, we know that X is equal to 0.00410 molar based on this part. So to find Kb, as we talked about before, so we are going to need the equilibrium concentration of ammonia, which is equal to 0.950 minus X, and where X is equal to 0.00410 as we determined, it is going to be 0.9459 molar. The concentration of the ammonium is just X, which is equal to 0.00410 molar. With these two information, we can find Kb because we know that Kb is equal to the concentration of the equilibrium concentration of the hydroxide ion multiplied by the equilibrium concentration of the conjugated base, in this case is ammonium ion, and divided by the equilibrium concentration of the base, and that is going to equal to 0.00410 squared divided by 0.9459. And this will give us a Kb of 1.77 times 10 to the negative 5. This is our Kb. Looking at the percent ionization, we can also define it in terms of the base concentrations. Ionization. So we talked about how we can do it for acids, and now we are going to be looking at how we can do it for bases. And it is still the same way. If we look at this, this is equilibrium concentration of hydronium ion and the initial concentration of the base. So now we talked about how we have the Ka and Kb. So remember, Ka is the right side over left side. So hopefully this is not an equation you will need to remember, and you can just look at the equation to find out how Ka and Kb is defined. So over here I'm rewriting how Ka and Kb is defined. And as you probably noticed that the A in the second equation, it doesn't mean base or acid. It just means that it's a random substance. And then we are looking at it in terms of acid and base dissociation reaction. So I know previously we used A for acids, but just remember in this case, A does not really stand for acid. Sorry, A minus. So this is the base, it gains a proton. This is the acid, it loses a proton. This is the acid, it loses the proton, and the base gains a proton. So between Ka and Kb, we can imagine that we can multiply them with each other. And then, so if we multiply Ka and Kb, then we can find that, okay. And I know for you, you're probably feeling like, okay, I want to skip this over. But again, I just want to show you where the equations come from because they are derived from one another. And I think that it's going to really help if we know where it arises from. And all these concentrations are equilibrium concentrations. I was just a little too lazy to write it. So we can see those cancel out. These two cancel out. So at the end of the day, Ka times Kb is the concentration of hydronium ion multiplied by the concentration of hydroxide ion, and that is Kw. So from Ka and Kb, we can find from Ka we can find Kb, and from Kb we can find Ka of the same substance, because remember, we're looking at the same substance A. And that is how we can find Ka from Kb and Kb from Ka of the same substance. So if you look into the table, sometimes it will only give you Ka or only give you Kb. Well, we know how to convert between one another. So over here is an example as to how we can go from one to another. And hopefully you can pause the video, try it yourself, and then we can come back and look at this together. The Kb for the nitrite ion, NO2 minus, is 2.17 times 10 to the negative 11. Calculate the Ka for its conjugated acid. So as discussed before, we know that for any conjugated acid-base pair, Ka times Kb is going to equal to 1.0 times 10 to the negative 14 for any conjugated acid and base pair. That means that if we have the Kb, we can calculate the Ka for the conjugated acid. So Ka multiply, which is the conjugated acid of an O2 minus. In this case, it is likely going to be the nitrous acid of Ka, because that is its conjugated acid, multiplied by Kb, 2.17 times 10 to the negative 11 is equal to 1.0 times 10 to the negative 14. So Ka, in this case, is going to equal to 4.6 times 10 to the negative 4. So again, the idea is pretty simple as long as you can relate the Ka and Kb of a conjugated acid-base pair.